Good morning students. Today we will study the concept of power system stability. So what is stability? It is the ability of an interconnected power system to return to its normal state or stable state after having been subjected to some form of disturbances. So to understand this concept of power system stability, we have to first study the concept of dynamics of a synchronous machine. For this, let us draw some construction. Let this be the x-axis. This is y-axis. Intersection 1, intersection 2. Let us assume this is the rotor. This is the rotor which is rotating with a angular speed of omega r. This is the rotating axis, and omega is the synchronous speed of the rotor, and this is the stationary axis. It is the reference axis. Let del be the rotor angle and theta be the angular displacement. Now for a silent pole machine, we know that theta E is equal to P by 2 theta M. Now differentiate this equation with respect to t. We get d theta E by dt equal to P by 2 d theta M by dt. Now we know that the rate of change of angular displacement with respect to time is nothing but the angular velocity. We know that the rate of change of angular displacement with respect to time is nothing but angular velocity, or we can say it as angular speed. So now we can write d theta E by dt as omega s and d theta M by dt as omega sm. M stands for mechanical angular displacement. So therefore now this equation becomes omega s equal to P by 2 omega sm. Now we also know that the kinetic energy is given by half I omega sm square. So from this equation we can get the value of omega sm. So put the value of omega sm from this equation to this equation. So half I 2 by P square omega s square, because we are taking the square of this omega sm term. Okay, now we can rewrite this equation as half I 2 by P square omega s into omega s. Now this term is m. M means inertia constant. This is the term called as inertia constant, where m equal to I 2 by P square omega s. So now for a two-pole machine, two-pole machine, put the value of P equal to 2. So we get M equal to I 2 by 2 square into omega s. So I, if you cancel these terms, it becomes 1 square, and 1 square is nothing but 1. So the value becomes M equal to I omega s, where M is the inertia constant, Now we have the another inertia constant term, that is H, and it is defined as megajoule of stored energy at synchronous speed to the, it is the ratio of megajoule of stored energy at synchronous speed to the MVA rating of machine, and this MVA rating of machine is generally taken as G, and this megajoule of stored kinetic energy at synchronous speed is nothing but kinetic energy at synchronous speed divided by machine rating is generally taken as G. So now therefore kinetic energy equal to GH, right? Kinetic energy equal to GH. So now we know that kinetic energy is equal to GH. So we have already calculated the value of kinetic energy. Kinetic energy equal to half m omega s. So we can write half m omega s equal to GH. Now simplifying this equation, we get m equal to 2 GH by omega s, and omega s is given by 2 pi n by 60, and n by 60 is nothing but frequency. So we can write this omega s equal to 2 pi f. Now put this value of omega s in this equation. So we get m equal to 2 GH by 2 pi f. So this 2 get cancelled. Now the equation becomes m equal to GH by pi f. This is megajoule, the unit of this m is megajoule second per electrical radian. And if we want this value in degree, then we can write m equal to GH by 180 f, and the unit is megajoule second electrical degree. So this is these two equations gives us the relation between m and h, where m and h both are inertia constant, where m and h are both are inertia constant. So in this way, today we have understood the topic of dynamics of a synchronous machine for understanding the concept of stability. Thank you.